So the first question is the question 4 from chapter 11. So the first one, can you do this, this table? Do you understand what this table is doing? The probability or proportion of time that second station use. So I think I don't have the number here, but as I recall, the question itself give you a relative number. I think something like out of 100 days where this guy predict that the probability is 0. Out of 100 days, in this case, 20 days these things happen, and 80 days it didn't happen, something like that, right? So that's why it's 0.2, right? Okay, 20% chance. And you do the same thing for probability 0.2, 0.5, 0.8, and 1. You understand this part? Okay? And basically this calibration graph did exactly what this number do. Okay? So for example, this first point, it means that here is the probability assessed by the manager, so the predicted number. In the class example, I give raining probability. Okay, so this is like I predicted that tomorrow's raining probability is 0%. So 0, and out of 100 days out of many days in the past, when I predicted that the raining probability is 0, actually about 20% of those days it rained. Understand? So there's why the height here is 20% or 0.2. Okay? And then for predicting, when the prediction is 0.2, the actual probability is about 30%. So 20% and the height here is 30%, something like that. And then the other 3 dots are draw according. This is the definition of calibration. So if you don't know how to draw this graph, you must not remember what's the definition of calibration. Otherwise, this is not really that hard. This is just simply pointing points by definition. Yeah, so if you still don't understand what I'm talking about, you should definitely read the textbook about calibration. Okay? And the yes.
But how do we calculate the number? Because it offers the numbers of days the manager predicted, how many percent it will rain.
So, since you have the textbook, so in the textbook it reads like out of 0. So the prediction here is 0, and 40 days it was the first station, and the 8 days was the second, right? So basically you add up these two numbers. This is out of how many days in total, and this is out of how many days the number of second stations used. So 8 out of 40, that's 0.2. That's what I'm saying. In the textbook, it gives you the number. You just need to calculate it. Any more questions? How about this Breyer score? You guys all got it correctly? No? Then you should ask, okay? And you can ask the questions. So in the textbook, or during the lecture, I defined the Bayer score as this. Bayer score equals what? Can someone tell me? If you don't know how to do it, go back to the definition. What is the definition of Bayer score? It's in the textbook. Can someone tell me? 1 minus x minus p power of 2, right? What is x? What is x? The event is a binary variable, equals to 0 if the event does not occur, equals to 1 if not occur, equals to 1 if occur. Okay? In this case, the event is, you can define it as if the second station is used, for example. Okay? And when I do this, I was referring it to a single event. A day's raining or not. So basically, if yesterday the prediction of whether it will rain today is 80%, then here the P will be 0.8. And do we have raining today? Yes, right? So X will be equal to 1. So the Bayer score will equal to 1 minus 0.8 to the power of 2, which is 1 minus 0.04, so it's going to be 0.96. If you don't understand what I'm writing here, you need to raise your hand now. This is, okay. So, do you understand what this means? This is the Bayer score. So this is the Bayer score, the same equation here. I just replaced x with 1 and p with 0.8. 0.8 is the prediction. X equal to 1 if the event actually occurs, 0 if the event does not occur. So I said that my story was, if yesterday the prediction of raining probability for today is 80%, then P is 0.8. Understood that part?
Yeah.
And then, do we have rain today? Yes, right? It rained this morning. So X is 1. So that's how you calculate it. Understood?
And how do you explain the results as you're getting?
How do I what?
How do you explain it? Like, what does it mean?
It means the prediction, the precision of your prediction. The higher it is, the better your prediction is. We were talking first about calibration, if you recall. And I told you calibration, I give you an example where calibration isn't the best best measure of precision, because I can say my prediction is that the raining probability of in Taiwan overall is, in Taipei, for example, is 70%. And because I know from the past data that on average every day's raining probability over a year is about 70%. So my prediction, if I made the same prediction of 70% over the whole year every day, 365, then my calibration will be perfect. But that's a bad prediction because it doesn't help you, right? Every day if I tell you the raining probability is 70%. Unless it's actually true that in a place where every day the raining probability is 70%. Otherwise it's not useful. Okay? And that's why we use a score. We want to create a score, or I don't even remember it's BR or BS, but it doesn't really matter. Does this score need to reflect the fact that the more precise my prediction is, the better the score must be. Okay? In the sense that if I made the same prediction, so for example, if in the past 5 days we're actually 1, 1, 1, 1, 1, and 0, 0, I should write this in a sequence. So 1, 1, 1, 0, 0, 0. 1 means raining, 0 means not raining. Okay? So if in the past 6 days, this is what actually happened. And my prediction was, the first prediction is I predict half for every day. The second one is that I predict 90% for the first 3 days, and the 10% for the last 3 days. Okay? Then, okay, the number here is not, I need to create a different number. It's not 90. I think it's somewhere like 75. Okay. 75 and 25% for last 3 days. Okay. In terms of calibration, the second one is actually worse. Because in the second one, I will draw a calibration graph like this. Prediction is either 25% or 75%. And when it is 25%, the actual probability is 0. If it is when the prediction is 75%, the actual probability that happened is 1. Right? And the best prediction should be aligned on the 45-degree line. So that's the line like this. Okay? But the first one, 50% every day, because the prediction is 50%, and on average it is true that the raining probability is 50%, right? So it will lie here, just 1 point. So the calibration wise, this one is better than this. This one is better. But which one do you actually prefer? The second one, right? The second one, although it's not perfectly good, but telling you 75% chance raining when it always rains is better than telling you 50% in those cases. And telling you 25% of chance of raining of those days who never rain is better than telling you that's 50%, right? Understood? Okay, so we need to create a score that reflects this difference, which actually make the second one better. That's why it has this part, x minus p, the fact minus the probability. So if the fact, here the fact is this, right? And the probability is this. So if the fact and probability is far from each other, we need to give it a penalty. That's why it's to the power of 2, it's squared. Okay, it means that the difference is enlarged. Okay, the bigger the difference, when the power is, it will be even bigger. Okay, become a punishment. Like I said, and I also mentioned this last time in one of the class before, not last time. But if you change this power to 4, that also works. It's just a different score. The Breyer score is just specific, the one that was the to the power of 2. Okay, and since it's the punishment, so it needs to have the minus there. And the 1 here is just to make it so that it's between 0 and 1. Okay, because x here is 0 and 1, 0 or 1. And the p here is between 0 and 1. So 1 minus or 0 minus something between 0 and 1 is still going to be 0 between 0 and 1. To the power of 2 is still going to be between 0 and 1. 1 minus that is still between 0 and 1. So the whole thing is between 0 and 1. So the higher, if it is 1, it means what? It means there's no punishment, right? It means x minus p is always 0. That's the only case where you can make the bias score 1. That's the best scenario, right? So x is always equal to p. What that means is the prediction I make is only 1 and 0. Basically, it's like when I made the prediction of tomorrow's weather, I'm going to tell you only two answers. Either it will rain or it will not rain with certainty. Okay? And my predictions are always correct. That's the best weatherman that you would want, right? In that case, the bias score would be 1 because x always equal to p. So it's x minus p is always 0. 0 to the power of 2 is still 0, and so on. Okay? More question about how to, is there any more question about how to calculate bias score as I just described?
So just,
Yes.
I understood the formula in the exercise.
Yeah, I haven't go to the exercise yet. So far, do you understand?
Yeah.
Okay. So that's calculate for 1 day. And in the example, in the exercise, it asks you to calculate the bias score, the average bias score for a bunch of days, basically. Okay? And to do this, you basically use a technique that you use in statistics many times in the past. It should be the case. So, for example, let me ask you this. So, if you know how to calculate the average, if I tell you in the whole class, the scores goes like this: 90, 80, 60, 70, 75. You know how to calculate the average of these, right? This sequence, right? But a lot of time you don't have a distribution like this. What you have is this. So 0 to 60, I have maybe 1 people. 60 to 70, I have 3. 70 to 80, I have 2. 80 to 100, I have 2. You see, and I asked you to calculate the average, the average grade for this class. You should have seen this before, right? And how do you do this? You basically assume a midpoint or average, right? So you basically assume everyone here get a 55, get a 30, because the average is 30. The average here is 30. The midpoint, basically. So here the average is 65, here the average is 75, here the average is 90. I assume everyone here get 30. Everyone here gets 65. Everyone here gets 75. Everyone here gets 90. And so give you 30, 65, 65, 65, 75, 75, and 90, 90. It goes back to this case. And you can actually calculate the average, therefore. Right? And here we basically use the same technique. So we have, now that I remember, in the first case, we have 40 days. Out of those 40 days, there are 8 cases where the bias score, where the second station were used, right? So there are basically 32 days that the first station were used, and 8 days that the second station were used. Okay. And then what you basically do is you assume that they were, so actually now that I think about it, it's not really the same technique anymore, because you basically assume that because when you calculate the Bayer score, you don't care about the order, right? You only care about what happened in those 40 days. So out of those 40 days, there are 8 days that the second station were used. So out of 8 days, that second station were used. And out of 32 days that the second station was not used. That's how the 8 and 32 came from. Okay? And why is there's a 0 here? This 0 comes from the fact that when, in this case, the prediction, out of those 40 days, the prediction was what? What is P? Out of those 40 days, what are the predictions? 0, yes. Do everybody understand what I'm saying? Okay. So out of those 40 days, the prediction was 0. And in those 8 days, X are 0, right? Yes, X are 0. Yeah. So, so like I said, you can define it either way. So X can be, so raining can be 1 or raining can be 0, either way, right? So the definition, it's whatever you like. So here in the solution, it defines X as 1 here. If used, the X is 1. And in that case, 1 minus P minus X to the power of 2 is going to be 0. Yes, right? So out of those 8 days, the score are 0. Okay? And out of those 32 days, the scores are 1. The other 32 days. And then we look at the other case where the prediction, there are totally 160 days, and the prediction were what? Prediction were what? What's the prediction? Point 2. I was here, now I'm here. Right? Do people understand what I'm saying? If you don't understand, please tell me. It's fine, but you need to understand this, because since you guys are a little bit confused here, I assure you this is going to be a similar question in your exam. Okay? So you need to really understand now. So P is 0.2. And when P is 0.2, so it's actually here. So when P is 0.2, the Bayer score, if used, is going to be 0.36. Can someone tell me how do I calculate this 36? So Bayer score is 0.36. So it's going to be 1 minus X minus P. P is 0.2, right? To the power of 2. So if used, I said X equal to what? 1. Okay, so it's 1. Okay? If used, X is 1. So X equal to 1 here, X equal to 0 here. So X equal to 1, then this become 1 minus 0.8 to the power of 2. That's exactly 0.36. Okay? Similarly, you simply replace that x with 0, you will get 0.96. So out of 160 days, there were 50 days where the Brier score there were 50 days where the Brier score was 36, and there were 110 days the Brier score was 96. Understood? Okay? And similarly, you can calculate this number accordingly. And were totally 600 days. So what I do is I add up the number and then divide it by 600. Take the average. That becomes 0.8833. Understood? Okay? Now here, so the last question asks you, if I simply make a prediction of 50% every day, what would happen? If I make a prediction of 50% every day, the Brier score is gonna be 0.75 anyway, no matter what happened, right? Because the formula is gonna be written like this. And if every day the Brier score is gonna be 0.75, the average has to be 0.75, right? So you will find that in this case the Brier score is lower than this one. So although my prediction wasn't that good in terms of calibration, in terms of Brier score, it's actually not that bad. Of course, I can do better because in this overall is there is a clear underestimation of the probability here, right? Because the 45-degree line is gonna be this one. So overall, it is underestimate. The underestimate. Questions? No? More questions on assignment 3? Assignment 4, what you just submitted. By the way, the solution is also already on E-class. I just uploaded it. No? No questions? Really? Yeah. Number 4. Part E. So, do you know how to draw the find the proper subgame? Do you understand my questions? So, do you know how to find the proper subgame? No? Okay. What's the definition of proper subgame? Proper subgame. You don't know? Okay. So here again, look, whenever you ask me a question, the first question that I ask back was always what? what is the definition of blah, 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 right? So because that was everything, again, that's the key. To learn this, to learn basically everything, the first thing you need to remember is the definition. So the definition of a proper subgame is you need to start from a node and contain all the branches that branches out from it. So if I start with this node, it branches out like this, right? It has to include everything, so that's the first big circle. And then if I start with this node, it branches out like this, right? So the first circle that I draw, the second circle that I draw will be like this. Similarly for this circle. That's how you define that's how you find all the proper subgame. Yes.
Do we consider that having 1 instead of 0 is better than both having 0 all the time? I mean, in a conclusion, like maybe Toshiba or Sony would rather have both of them have 0 rather than the concurrency have like a strong advantage.
It would not. So what you're talking about is what I mentioned last time. It's called other regarding preference. You care about what other people have.
Yeah.
I'm saying there's no such thing in game theory. Okay? Never such thing. Unless I specifically tell you there is. The traditional game theory, there's no other regarding preference. So you only care about your payoff. You're getting 1, it's better than 0. That's it. Okay?
I don't understand. The question is use backward induction. What means like use backward induction to solve the subgame problem?
So you also don't know what is backward induction? That's the question, right?
Yes.
Okay. So is it the case that you were not in the class during that week?
Yes.
Or okay. But please make sure you go over the video. Okay, it's there. Okay. So the definition of backward induction is simply go from the back end of the game, the end of the game. So the end, there are 2 ends here. One is here, one is here. Either way is fine. Here, the Toshiba is the second mover. So the payoff he gets is the second number here. Okay? So in that case, Toshiba would prefer getting a 1 other than 0. And Toshiba here would prefer a 3 other than 0, other than 2. And then for Sony, he would prefer 3 over 1. So that's backward induction. Okay? And based on backward induction, you find out the strategy is Sony would choose I, which is invest heavily, and Toshiba would choose S, which I forgot what that stands for. Okay. And so Toshiba will choose S if Sony choose I, and choose I if Sony choose S. That's here, what's written here. Again, you can write something like this, represent the subgame perfect equilibrium, but do not write, for example, 3, 1, and say this is SPE. This one guarantee you a score of 0. There's no partial score for this one. Okay? That's the equilibrium payoff, not the equilibrium strategy. Strategy and payoff are different. Period. Okay? And you find out there were actually 3. In the previous question, you find there were 3 Nash equilibria. And the question asks you why there are. So here you only find one of them are SPE, right? So you find 3 NE, and out of these 3 NE, there were only one that's SPE. Okay? And the question was why the other two are not SPE, basically. And this is what I mean by credible or non-credible in the lecture, right? So, for example, why it isn't Nash equilibria to play so Toshiba irrationally play S after Sony play. So why? So one of the Nash equilibrium that's not subgame perfect is this one. Sony will choose I, and the Toshiba will choose S no matter what. Okay? This one is Nash equilibria because Toshiba still getting, Sony is still getting 2. 3 is still better than 2, so Sony doesn't have the incentive to move. And because Sony is actually choosing I, so no matter what Toshiba do, it doesn't change the payoff either. So this is Nash equilibrium, that's true. But in this part, what Toshiba do is non-credible, meaning it's irrationally for Toshiba to play S because he could have win 3 instead of 2. Okay, that's just one example. The other one goes the same logic. Questions? No? Other questions? No? Really? Okay. Then we will have a longer break until 2 o'clock. If you still have any question, you can come to me. Okay?